So, we have been discussing the appearance of systematic absences depending upon the lattice types, and here is a list of all possible lattices in the 7 crystal system, which will ensure the number of coordinates in the coordinates of the lattice points, which are shown here, and the type of systematic absence we get as a consequence of the centering of the lattice. So, the primitive lattice obviously therefore will not have any systematic absences. What it means is that all the primitive lattices which come in all the 7 crystal systems will not have any systematic absences associated with general reflections. So, if you take reflections H, K, L, all values of H, all values of K, all values of L, then the systematic absences associated with a primitive lattice will be none, in the sense that in principle all the reflections allowed are present. Of course, the primitive lattice may carry information about the symmetry, which could be having a translational component like a screw axis or a glide plane. We shall discuss that later on. But at the moment, whenever there is a primitive lattice and no translational component associated with the symmetry elements, like for example P1 and P1 bar, P2, Pm and things like P2 by m and things like that, there will be no systematic absences. So, systematic absences come up with the centering. So, if there is a centering, we will have the systematic absence coming in terms of the values which adds on to the axis. So, whichever axis to which the half adds on, those axes will show the systematic absences. So, we get K plus L equals 2 n plus 1 for the A centering, B centering H plus L 2 n plus 1 and C centering H plus K 2 n plus 1. We have discussed the appearance and how it influences the expression for the structure factor in earlier classes, and therefore, right now we will see that for the face centered, which we discussed with the example of zinc sulphide, HKL neither nor all odd nor all even. That means they have to be in such a way that all the 3 indicated here above should be simultaneously satisfied for a reflection to be systematically absent. What is listed in the international table, which we will have a look later on, are not the systematic absences, but systematic presences. So, that is something which we should remember when we look at the international tables for reference. So, having seen this, we now go and see what are the systematic absences which come due to the presence of translational components in the symmetry associated with the space group. So, the space group, the lattice type we have seen. Now, let us say there is a space group which is associated with an A glide. Let us take an example of a primitive lattice with an A glide. It could be an I-centered lattice with an A glide in a monoclinic system, or say the centering could be also a reason which is introducing the A glide. So, if there is an A glide which is now in any of the directions associated with x, y, z, suppose there is a glide which goes through the origin and is parallel to 0, 0, 1, the plane 0, 0, 1, the z axis, then you see that x, y, z, every point x, y, z will give rise to a half plus x, y and z bar. So, that means the A glide operation takes the point x, y, z to half plus x, y, z bar, and if we operate again on this one, the A glide will go back to that. So, that is the group which we are considering. And what happens to the structure factor expression? So, we write the f of HKL expression as before. It is 1 to n Fn exponential 2 pi Hx plus Ky plus Lz. And we also have, due to the second equivalent position, because again these two are equivalent of each other, we separate them into two parts. So, the summation goes from 1 to half of n and fn exponential to pi hx ky plus lzn plus exponential to pi I. This is half plus x. So, half plus h adds on here, half h plus hxn plus kyn and minus lzn, and this can be simplified and written as sum over 1 to half of n f of n exponential 2 pi I hxn plus kyn exponential this quantity plus exponential that quantity. Now, remember in the previous case when we were discussing the C-centered lattice, we had expressions of on the other side of the common factor, which involved only exponential to be raised to a integer. In other words, we had expressions of this kind, exponential 2 pi I h by 2 kind of thing, but we did not have any of the independent axis that is associated with it. So, therefore, when we have an A glide parallel to 001, we look at not the general reflections. So, there will be no general systematic absence. For example, PA, if it is a space group, primitive will not give any systematic absence associated with general reflections, but the A glide will give systematic absences when L is put equal to 0. What happens when L is put equal to 0 is this expression will now simplify. So, we write the expression for f of hk 0. That means, we are now looking at only the projection reflections. We look at different values of h, different values of k, but 0 value for the z value. So, whenever this is 0, it is a projection down the z axis and the expression becomes 1 to half of n f of n exponential 2 pi I hxn plus kyn multiplied by 1 plus exponential pi I h. You see now what I was mentioning has happened. In this case, we have therefore only the integers in this part of the flower bracket. And when we have the integers in the part of the flower bracket, we can calculate mathematically the value, and that turns out to be 1 plus minus 1 to the power of h. So, depending on the value of h, this value will be either 2 or 0. So, it will be 1 plus 1 or 1 plus of minus 1, which is 0, or 1 plus minus 1 to the power of h, that will make it minus 1 or plus 1, and whenever this is plus 1, it will be that h equals 2n plus 1. That means, all odd values of h, this particular value 1 minus 1 will cancel out, and therefore, this will become 0, and therefore, the value becomes 0. So, the systematic absence associated with a glide passing through the going is along the z axis or parallel to the z axis. A is perpendicular to the 001 plane, then f of hk 0 is 0, for which h odd is absent. So, h equals 2n plus 1. So, this therefore tells us that we can have systematic absences due to glide operations. We have already seen how many glide operations are possible: A glide, B glide, C glide, N glide, D glide in a special situation. So, all these glides therefore will give rise to systematic absences depending upon the projection reflection. So, it is only the projection reflections which will show you systematic absences, and we will examine it a little more closely. Let us take all possible A glides. If you have all possible A glides, the type of glide is A glide, then the translation is A divided by 2. Whenever A is involved, it is h equals 2n plus 1, which is systematically absent. For the B glide, it is B by 2, k equals 2n plus 1. And of course, we cannot have a C glide parallel to 001, we know that, and therefore, there is no C glide associated with the glide planes parallel to 001. But we can have C glides parallel to the other two directions. That means, to other two planes, 010 and 100 can have C glides. 001, which is a plane which is associated with the direction of z, it is perpendicular to the direction of z. So, C glide is not allowed, because the translation has to be half along that particular direction. So, we have therefore the A glide and the B glide. We can also invoke the presence of the N glide, which is A plus B by 2. Then we will have the systematic absence h plus k to n plus 1. But all these systematic absences occur in only projection reflections. Projection reflections associated with these. So, in this case, for example, it is hk 0. In this particular case, what would be the thing I want you to find out? It will be hk0, but this time the k is equal to 2n plus 1. So, the systematic absences are all in hk0 reflections. So, in the case of A glide it is h odd, in the case of B glide it is k odd, in case of the N glide it is h plus k odd. And in case there is a diamond glide, which we have not discussed, which is probably out of the scope of this course, we will not consider this, but it will also have systematic absences as shown below. It is just for our record. We are not going to discuss how it turns out. So, if that is the case, what are the types of glide planes we can think of? We can think of glide planes parallel to 1 0 0 direction, which is along the A axis, glide plane parallel to 0 1 0, which means it is B, and glide planes parallel to 1 1 0, which is along the diagonal. So, we have listed therefore the planes which are in these directions, and the glide planes which are along with the 1 0 0 can be B, C, N and D. 0 1 0 is A, C, N and D. Of course, we can always have 0 0 1, which we already discussed. So, we have not put it here, and the glide plane 1 1 0, it can be C, B, N and D. And the set of reflections that will get affected in the case of the glide plane parallel to the plane 1 0 0 is 0 k l, glide plane associated with 0 1 0 is h 0 l, h o l, and glide plane this will be h l. And so, the systematic absences are listed here, and these will be the condition. Here you see on the right side we did not list the systematic absences, but we have listed the systematic presences. So, k E1 only present, L E1 only present in the example of a glide plane which has a B glide and a C glide respectively. It is k equals 2n, L equals 2n. So, the conditions for getting the reflections measurable are given here, and this is what you will see in the international tables. But for the discussion sake, which we have done so far, the lattice centering, and then also the A glide, which we have discussed in detail. We have discussed the systematic absences, because it is always good to see what is absent than what is present. I mean, that is normally the logic. You know, there is a statement that if in an audience in the classroom, for example, if all students are present, their presence will be ignored. Those who are absent, they will be noted. So, it is something like that. So, systematic absences therefore are very crucial to notice, and that is why systematic absences are discussed before. But what is present is more important from the point of view of the diffraction condition, and therefore, the presences are listed here. So, international tables for crystallography will list only the systematic presences, what are present systematically. All right. So, this is as far as the presence of the glide plane is concerned. So, we have seen the lattice centering, and now we have seen the glide planes. So, glide plane give systematic absences associated with projection reflections. The general reflection systematic absence give the lattice centering information. So, the next obvious choice is the presence of the screw axis. So, what is the plane that it can affect? It can affect not the planes, but axial reflections. By axial reflections, I mean it will affect the h 0 0, k 0 0 and L 0 0 with respect to a HKL plane. So, it is therefore the axial reflections, they define the h direction, the k direction and the L direction, h equals 1, 2, 3, 4 like that. So, what happens in such a situation is, again we have to write the general expression for the structure factor and then evaluate the structure factor features associated with it. Let us look at it in a careful manner. So, in this case the systematic absence we now consider produced by screw axis. Please notice the nomenclature. I am just reminding you that when we put in square bracket, it represents the direction. When we put in ordinary brackets, it represents the plane. So, the previous representation was with respect to the plane, and this is now with respect to the direction. So, this is along the z direction. So, when we talk about the screw axis are parallel to the 0 0 1. And when we talk about the glide planes, and we have written parallel to, that it will be parallel to the planes 1 0 0, 0 0 1, and 0 1 0. So, systematic absences produced by screw axis. Now, the direction is 0 0 1. So, x y z now will become x bar y bar, and you see since the translation component is along the z direction, we have a half plus z in that direction. So, this screw operation again operated will take you back to x y z, defining the point group. So, whenever you have a crystal system like P21 for example, a primitive lattice with 2 1, then you will have this systematic absence coming up. How it comes up we will discuss in a minute. So, again we write the general expression for f of HKL. You see again we have to consider half the number of total reflections, because one half will obey this, the other half will obey that, and so the expression now is f of n exponential 2 pi I h x plus k y plus L z plus exponential 2 pi I minus h x minus k y plus half L plus L z n. So, we now take out the common factor and rewrite this expression. The common factor here between these two is exponential 2 pi I L z n f f n. So, this therefore becomes 1 to half of n f n exponential 2 pi I L z n and exponential 2 pi I h x plus k y as far as this first expression is concerned, and as far as the second expression is concerned it is minus of h x minus of k y plus half of L. So, the same logic as we defined in the previous case, that we would like to have a expression which will essentially depend upon integral values to take the exponential, then we can calculate it mathematically, and so we separate it out. The way to separate it out is to put h equals and k equals both equal to 0. So, if h and k are both equal to 0, we have only reflections of the type 0 0 L. So, the f of 0 0 L now will be having a formula reduction which is going from 1 to half of n, f of n exponential 2 pi I L z n multiplied by this, since h is 0 k is 0, this will go, and therefore, you get 1 plus exponential pi into I into L, and we know this value can be minus 1 to the power of L, and therefore, it has to be again the same logic that whenever L is odd, f of 0 0 L will be absent. So, the systematic absences associated with the screw axis essentially affects only the axial reflections. So, the reflections which go along the definition of the axis, either h or k or L, and so we can now write down those expressions and see how it comes about. So, we can have screw axis in variety of crystal systems, as we know. We can have 2 1 screw, we can have a 4 1 4 3 4 2 in a tetragonal system, we can have 3 1 and 3 2 in a trigonal system, we can have 6 1 6 5 6 2 6 4 6 3 in an hexagonal system. So, these are all the possible screw axes we can have in a crystal system, and therefore, we now look at the corresponding systematic absences if the screw axis is parallel to the z direction. So, that will affect the 0 0 L reflections only, and the condition is on L value, and that condition on L value for 2 1 screw axis, the translation is along the z direction. So, it moves along the c axis, it is c divided by 2, that is the translation associated with the screw axis. So, we get therefore the systematic absences to be L equals odd. So, all odd reflections will be absent. What is interesting is the systematic absences follow a certain trend among the tetragonal and the trigonal and the hexagonal systems. That is because in all these cases the unique axis is z, and therefore, the screw axis is parallel now to the unique axis. Since the screw axis is parallel to the unique axis or along the unique axis, the systematic absences will develop differently depending upon the nature of the screw axis operation which we invoke. For example, if you have a 4 2 axis, for all practical purposes a 4 2 axis is effectively a 2 1 axis, and therefore, you will have only L odd absent. So, suppose there is a space group P 4 2, then the systematic absence in that particular space group will be just 0 0 L odd absent. On the other hand, if you have a screw axis 4 1 and 4 3, these two axes are now in two opposite directions, but representing the same effective positioning of the atoms, except that the handedness of associated with 1 and 3 will change, and therefore L is going to be not equal to 4 times n. That means whenever L is 4 times n, you will get the reflection. So n can be equal to 1. So you get reflections like 4, 8, 12 and so on. Multiples of n can take values 1, 2, 3, 4 etc. So it depends upon the length of the unit cell. Suppose the unit cell length is about 20, then you will have the reflections coming only for those reflections 0, 0 L, which is L equals 4, L equals 8, L equals 12, L equals 16 and L equals 20. So you will get 5 reflections along the axial line. So you can easily observe when you look at the reciprocal lattice image which you have measured, and particularly if you have done a photographic measurement, it is easily seen in earlier days. But nowadays you can always have a program which looks into the possible systematic absences once you have a collection of all the HKL reflections. So you have done the experiment, you have put the crystal on the beam, you get the diffraction done, and then you have the reciprocal lattice image. The images of the reciprocal lattice you examine after indexing them with respect to H, K and L. We will see how that is done after probably in a couple of classes. We will know authoritatively how to do that. And once we have these HKL information available to us, we examine the values of HKL, and the systematic absences will show if there is anything. For example, in this case all values of L equals 4n will be present. So we can easily identify as far as 0, 0 L is concerned whether it is 4, 1 and 4, 3. For both it is the same systematic absence. Same is true with the 3, 1 axis and the 6, 1 and 6, 5. You see L not equal to 3n, L not equal to 6n, and in case of 6, 2, 6, 4 also it is L not equal to 3n. So what it means is that by looking at the systematic absences associated with these crystal systems, you cannot decide the space group. Please note the point. Suppose there is a space group which is P31 and then a crystal system which goes into P32. By just looking at the systematic absences, you cannot say whether it is 3, 1 or 3, 2. Same is true with 6, 1, 6, 5, same is true with 6, 2, 6, 4 and same is true with 4, 1, 4, 3. So only when you have the half the translation of the length, for example 6, 3, for example 4, 2, because there is no half translation possible in the 3-fold axis. So 3/6 is 1, effectively if you divide this by 3 it will become 2, 1, 4, 2 you divide by 2 it will become 2, 1 and 2, 1. So the systematic absences are all identical, they are L equals 2n plus 1. So having seen this, we will see what happens in case the systematic screw axes are in different directions. So screw axis is parallel to A, screw axis is parallel to B and screw axis is parallel to 1, 1, 0. Whenever the screw axis is parallel to that direction, that particular direction only is affected. That means H 0, 0, H equals 2n and H equals 4n are present in these 4 crystal systems. In these 4 crystal systems, if the screw axis is B, we will see OK 0, K equals E1 or K equals 4n systematically present. So these are the present conditions. This is what we mean by conditions. In fact, that is what is written in the international tables as well. Screw axis parallel to 1, 1, 0, that is quite possible, and then you have therefore the systematic absences H, H 0. This is possible in tetragonal systems because you have A equals B in a tetragonal system. So you can have a 2, 1 screw axis parallel to 1, 1, 0 direction. So the crystal systems could be ideally identified based on these systematic absences. So essentially we have now covered all the symmetry elements which will have translational components. The centering information that is associated with the lattice will also give half additions and so on, and therefore we have these systematic absences. We have systematic absences due to the glide planes. We also have systematic absences due to screw axis. So these translation components which are present only in crystals, you see that is a very important point to remember. These systematic absences are present only in crystals and they affect only diffraction, and therefore it allows for a unique determination in most cases of the space group. Just to give you an example, suppose there is a space group P21 upon C. For the primitive you get no systematic absences, so you will have all HKL reflections present in principle. It is not necessary that all HKL values should be measurable. Some of them may be weak, some of them may be strong, and we know when it is weak, when it is strong by our previous discussions. It depends upon where the atoms are sitting in the unit cell. The contribution to the diffraction, the intensity contribution to the diffraction is coming from individual atoms which are inside the unit cell, but the measurement which we do is with respect to the plane. So, what is it that is coming out from the plane, and therefore, we consider this formula d capital HKL by small d HKL and calculate the values that come to the intensities based upon 2 pi Hx plus Ky plus Lz, and therefore, we have this general formula which will allow us to calculate the intensity. So, the intensities need not be present for all possible HKLs. Some of them may be absent, some of them may be present. Some of them may be absent because the waves coming out successively interfere such that they destructively interfere. Okay. So, when they destructively interfere, we will not get any intensity. It is not a systematic absence. The systematic absence should be throughout the data. What I mean to say is, watch my words carefully. If HKL, H plus K odd is absent, it will definitely tell you that it is a centered lattice. But by chance in a general HKL data, some H plus K odd may be absent, but it is not systematic. That is allowed, then it is still a primitive lattice. So, only when all the reflections of your HKL collected obey these conditions, then only you can say this as a symmetry. This case becomes very, very crucial in case you have a monoclinic system, for example. In case of a monoclinic system, it may so happen you are looking, let us say, at the unique axis B, and it may so happen the unique axis is about 4 angstroms. You may have A and B very large, but C axis is 4 angstroms. So, if there is a 2-1 screw axis associated with the B direction, then what would be the systematic absences? The systematic absences will ensure that only 2 0 0 and 4 0 0 sorry 0 2 0 and 0 4 0 will be present. So, 0 1 0 and 0 3 0 will be absent. That is the extent to which we can go, because we can measure only 2 reflections. In fact, we can measure 4 reflections, 0 1 0, 0 2 0, 0 3 0, 0 4 0. So, we have 4 reflections at our disposal along the C direction, along the B direction, along the unique axis B. So, there are 4 reflections 0 1 0, 0 2 0, 0 3 0, 0 4 0. So, if they are to be systematically absent and give rise to the presence of a 2-1 screw axis, we have to measure, we should be measuring only 2 0, 0 2 0 and 0 4 0. They should come with some intensity. It may so happen the atoms and the molecules inside the crystal may so arrange themselves that 0 2 0 and 0 4 0 may also become very, very weak, so weak that we cannot measure them. Then you will see all the 4 being absent. Okay. Or in the case of a system which has no screw axis, you may measure, let us say, 0 2 0, 0 4 0 as possible reflections. It may so happen the atoms again arrange themselves, even though there is no 2-1 screw axis, such that the contribution to 0 1 0 and 0 3 0 is very, very small. Then it looks as though there is a systematic absence. So, these are all pitfalls in uniquely determining the space group. So, determination of P21 with a unique axis B very small is a question, and in such situations we might have to look at the structure determination, and once we determine the structure, in fact determine the structure in both space groups P2 as well as P21, and then decide which is the space group into which it goes into. So, the determination of the structure then becomes crucial to identify the presence of the 2-1 screw axis. So, that is where we have to be a little cautious, but routinely if you have got a P21 upon C, it will have 2 systematic absences 0 K 0 K odd absent and HOL L odd absent. If HOL shows a H plus L odd absent, then it will be an N glide. So, we can uniquely determine the space group P21 upon C or P21 upon N by just looking at the systematic absences. As I said, primitive will not give any systematic absence. So, you will have all general reflections present. Then you look at the projection reflection. So, systematically you take the data, arrange it in such a way that you have all the general HKL the projection reflections and then the axial reflections. And the projection reflections, if you look at now, they will have systematic absences corresponding to the C glide. That means HOL, L odd absent. So, the glide planes will affect the projection of the along the plane. That means it is 0 along that particular direction where the axis is located. That means if you have, in the case of a monoclinic system, we have a 2 1 and a C, the unique axis is B. So, about the unique axis we have the 2 1 screw, so 0 K 0 K odd, and about the unique axis we have the mirror plane perpendicular to that, because the point group symmetry is 2 by M for P21 by C. So, we therefore have the systematic absence coming with respect to HOL, L odd absent. So, space groups like P21 upon C can be uniquely determined, and this is an advantage we have, because this particular feature will enable us to identify the space groups uniquely. So, for a simple discussion, many space groups belonging to different crystal systems can be uniquely identified by an examination of the HKL reflections. It is only those in which there is no translational component involved, these space groups are not identifiable by systematic absences. So, those space groups of course have to be identified whether they belong to the system, and what is the, for example, what are the symmetry elements that are associated with it. Take for example P2 and PM. It is very hard to distinguish between P2 and PM, because we do not have systematic absences. So, of course, there are ways and means in which we can identify probably one of the space group to be correct. We will discuss that later when we look at the intensity statistics. See, since intensities come from the scattering overall of the unit cell, so it does not matter in principle to the intensity the orientation of the planes. The intensity is coming from the electron density, and the electron density is continuous in the space. So, the way the intensities distribute themselves among various, let us say, values of sin theta by lambda, because we know that is the one which controls it, because scattering factor falls off with respect to sin theta by lambda asymptotically. So, since scattering factor falls off with respect to sin theta by lambda asymptotically, we have a dependence of the intensity on that value of that particular atom, and so the intensities will fall off with respect to sin theta by lambda. Apart from that, the intensities therefore distribute themselves into various regions of the scattering angle. So, there is a statistical evaluation that is possible for the intensities. It so happens, for example, if you have a space group P1 and a space group P1 bar, the distinction between P1 and P1 bar is fairly straightforward in the context of intensity statistics, because the intensity distribution will be different in case of 1 compared to the distribution in case of 1 bar. And this we will discuss when we do the scaling operation and how to put the intensities on an absolute scale. At that time we will discuss this issue, because it is at that time we can distinguish in such cases where systematic absences are not available. We have to find out the nature of the space group. So, whether P1 and P1 bar there is a triclinic system, whether the crystals are now going into a centric system or a non-centrosymmetric system, can be identified only by an analysis of the intensity statistics which goes along with it. So, to summarize all the issues done so far, we have identified systematic absences with respect to the lattice centering. So, we have identified systematic absences with respect to the glide planes to be with those of projection reflections, and with the screw axis with those of axial reflections. So, once we accumulate a data, collect the data after doing the diffraction experiment, we need to analyze the HKL reflections for this systematic presence or absence. And if this is nicely satisfied, we can uniquely determine the space group. If it is not nicely satisfied, we can still have an ambiguity in the space group. We can still identify the space group, but we can say this is this or that. For example, we discussed just now the possibility of 3,1 and 3,2. So, we can say, well, the space group is P31 or P32. but we are not sure whether it is 3,1 or 3,2 as of now. And those are, in fact, 3,1 and 3,2 are known as enantiomorphous space groups, and it is required to do the structure in both and finally identify which is the realistic space group associated with 3,1 and 3,2.